acid and base equilibrium. Before we begin, let me give a quick shout out to the three amigos. You know who you are, so there's your shout out. And we're going to begin acid-base, chapter 17, equilibrium. Now, chapter 16, we took just an acid and put it in water, and we saw what the pH was. And we put a base in water, and we saw what the pH was. Or we took a salt and put it in water to see what the pH was. Now we're actually going to have an acid and a base put together, and we're going to be seeing what the pH is. So that's really what chapter 17. So it gets more complicated. As long as you stay with me, you should be okay. And I've already should have already uploaded this PowerPoint, so I'm going to click through most of this, and you can pause and write down everything. First thing, it's called the common ion effect. If you have something that has a common ion in it, so this is acetic acid, and this is its conjugate base acetate there. That's a common ion. They both share the acetate ion there. So if I were to take this solution, this is one way to write it. Remember, you could write it with not the water in it, and this would be H plus instead. So that's a different way to write it. But if I were to take and put sodium acetate into the solution, that this is already at equilibrium, that's going to give me some acetate ions. So it's going to, just like Le Chatelier's principle said, if we were to increase on this side, it would actually cause it to shift to the left, and more of the acetic acid is going to be together, meaning it's not going to break apart as much, so it's not going to be as strong an acid if we put it in the sodium acetate as if we were to put it in just pure water. And so because of this, it says equilibrium composition would shift to the left and the degree of ionization would decrease. So we're going to look at a problem like this. Guess what the sodium's doing? Even though we've got sodium here, it's just spectating. It is that common acetate ion, so it's increasing the acetate ion here. So here's our first problem. First problem says, what is the pH if we had 0.3 molar acetic acid? What's the percent ionization of the acetic acid? So this is just acetic acid in water. So this is just a normal Rice equation. And so this was what last chapter was all about. Again, the other way, we could put plus water, or we could just break the hydrogen off. And this starts out as 0.3 molar with 0, 0. X. So these were the easier run-of-the-mill Rice equations. You end up with x squared, 0.3 minus x equals 1.8 times 10 to the negative fifth. We will solve for our x, and we will find that the x is 0.00232 molar, and that's our H plus, so our pH would be 2.63, and our percent ionization is always your amount that it's changed, x, divided by the I, 0.77%. So we did that last chapter. So this is if we just put acetic acid into water, what it would look like. Well, what if we put acetic acid not into pure water, but something was already there? So then that leads us to our second type problem here. So what is the pH of a solution made by adding a 0.3 mole of acetic acid and 0.3 moles of sodium acetate to enough water to make a 1 liter solution? First thing, we want to change our moles to molarity. Of course, it's 1 liter, so it's going to be a 0.3 molar solution of sodium acetate and 0.3 molar acetic acid. We're also going to figure out the percent ionization. So I'm going to have to go to a blank page to be able to work this one, so I'm going to click and go. So maybe you'll pause this and write that down if you need to, but I'm going to go to a blank page. First off, if I try to write an equation with these two, they're not going to chemically react with one another. The reason they're not is you can see that they have the common ion there. And if they have a common ion, they're not going to react with one another. If I try to double displace this, I'll get the same answer. But what's going to happen is the fact that there's some acetate ions there, it is going to mess up the equilibrium that acetic acid is trying to establish with the water. So this is going to be a Rice problem. So you start out with 0.3 molar of this. In the beginning there's none of this, but actually there is some acetate, so we actually have a number here. This is the sodium acetate, but the sodium is just spectating. It's not really, so it's just a spectator, so we do have some acetate ions. Since this is 0, you do have a plus X here, and you do have a minus X here. So you end up with x squared over 0.3 minus x, and we're going to set that equal again to the Ka, because this is for that acid. And we'll solve. Uh-oh. I already see I made a mistake. Getting in a hurry there. Didn't bring that down. So sorry about that. Knew something was looking weird. Now we're looking a little bit better. You can put that in solver. Now we're all ready. I was doing like the other type. Or if you notice something, this is to the negative fifth, so you could actually scratch through the minus x on bottom and the plus x on top. Do you notice something here? It's 0.1 and 0.3 and 0.3. So they'll cancel. So your x is going to be 1.80 times 10 to the negative fifth. Does that happen all the time? Well, no, not. But when they're the same concentrations, that'll happen there. So now I could find the pH by taking the negative log of that, and you will find the pH has gone up to 4.74. You could find the percent ionization, again, by the x divided by the I times 100, and it's 0.006%. So what has happened is less of it is breaking down because the reaction has actually shifted this way. So it's going to be staying together more than it will be breaking apart. So the pH went up because there's less hydrogen ions in the solution. So really not much harder, other than the fact that instead of them being 0, 0, they actually have a value there. So I'm going to click through. Next is just a bunch of definitions. A buffer is a solution that resists a change in pH. We have buffers in our body that help us maintain homeostasis. A buffer is made of either a weak acid and its conjugate base, so meaning its conjugate salt, or a weak base and its conjugate acid. That's how you're going to be able to tell. The one we just looked at, this acetic acid and sodium acetate, was a buffer solution because it had a weak acid and it had its conjugate base in solution together. So what's important about a buffer, it contains an acid part and a base part, and that's what makes it do its buffering in our systems. Again, you can pause this and write that information down, or you can just get it from the PowerPoint, but I'm going to continue on. So we have an equation like this. It says, what is the pH of a buffer? That is 0.12 lactic acid and 0.1 sodium lactate. Again, they're sharing a common ion with one another, and their common ion is that lactate, so they're not going to react. But what's going to happen is that sodium lactate is going to mess up this guy's equilibrium, trying to reach equilibrium with the water. So we're going to start out with 0 here. This one is 0.1. This one's 0.12. So looking very similar to, and we're going to have minus x plus x plus x. 0.12 minus x, x, 0.1 plus x. On the top, we'll go x, 0.1 plus x. On the bottom, 0.12 minus x. And that's going to be set equal to the Ka, 1.4 times 10 to the negative fourth. You can mark through these, and you cross multiply and solve. You will find your x. I'm going to switch my page. Your x in this case will be 1.68 times 10 to the negative fourth. And if we look, here's our H plus again. We'll take the negative log of that, and you'll find your pH is 3.77. So, works the same. It's just we're just calling it a name. So you'll know it's a buffer if it is a weak acid and it's salt, or a weak base and it's salt. So this one was a buffer, and the one before was his buffer. Now I want to show you something that's not a buffer. That is an acid and it's salt. And they do share a common ion here. But the difference is this is a strong acid. So this will not ever reach a buffer situation. The main reason is this guy breaks down 100%. And this is not going to disrupt his equilibrium because it doesn't do equilibrium. It's not going to shift it back the other direction. It goes to completion. So those ions will be just floating around. Also, this is a neutral salt. So a neutral salt's not going to increase or decrease the pH either. Okay. So another one next is called the Henderson-Hasselbalch equation. You'll like this equation a lot. It's pH equals pKa plus the log of the bases on top and the acid on the bottom. And you might want to write yourself a note. This is used for buffers. This is what this is used for. And anytime you have a P in front of something, that just means to take the negative log. So we'll be taking the negative log of the Ka. That's what pKa means. pH means negative log of H, pOH, negative log of OH, so pKa, negative log of Ka. So we could go back to that previous problem. Let me go back. And this is a buffer solution. And if you can recognize it's a buffer, you honestly don't have to write it. Now you can if you would like, but you can say, oh, this is a buffer. Let me just plug into this equation. Negative log of the Ka plus the log of the base, which in this case the base is a salt, but the conjugate base in this case goes on top, the acid part goes on bottom, and when you open up, that will open up a set of parentheses. You should see 3.77 is your answer. So simple as that. It might be 3.78, 3.77 and 3.78. You could go back and do it on that first problem that we did. Is 1.8 times 10 to the negative fifth, the very first one with the acetate. And it was a 0.3 for both of them. So our base was 0.3, our salt was 0.3, and our acid was 0.3. Well, 0.3 divided by 0.3 is 1. If you took the log of 1, this equals 0. So basically this falls out of the equation. So it's just a negative log of that, which is what we ended up doing when we worked that problem. And this is what we call the best buffer situation, when the salt and the acid or the salt and the base have the same molarity. That's when the system will buffer the best, which is what the next slide is saying. Buffers are most effective when the concentration of the acid and the conjugate base, or the base and the conjugate acid, are about the same molarities. So basically what happens is this comes out of the equation. So this is when it's best, when these are the same. And you can actually select a buffer. If you had a list of buffers, if you wanted a certain pH, you could take the negative log of all the buffers, and if it's the one that's closest to your pH would be the best buffer for the solution that you're looking for. And then we need to know human blood buffers around 7.4. Part of your assignment is to read page 651, and I want you to read about the buffering system of your blood. And there's some vocabulary words from that reading assignment. So you want to read page 651 and read about the human blood and what happens if it goes higher than 7.4 or whether it goes lower than 7.4. And we can do stupid things to our body, and we can actually kill ourselves if we mess up the buffering system of our body. Okay, I'm just going to click through this particular slide, and you want to stop and you want to copy this. This is all the steps to the problems that we're about to do. Whoops, let me go back. So you want to stop, pause this, copy this, because this is all the steps that we're about to do. But the job of a buffer is to resist a change in pH, and it does that by, if an acid gets put in, the acid will react with the base part of the buffer. If a base gets put in, it will react with the acid part of the buffer, and they'll neutralize whatever we add, as long as we hold within the buffer capacity. So this is going to be our example problem. This is the same scenario we had before with that acetic acid. And it says so we've got a buffer up here with acetic acid and sodium acetate. And this time, and rather this buffering, which it had a pH of 7.4, that was our pH earlier. That was the first problem we did. we're going to see what would happen if you add 0.1 moles of sodium hydroxide. Now, if we try to figure out the pH of 0.1 moles of sodium hydroxide is a pH of 13. So we're going to add something that has a pH of 13 into this buffer solution and see what would happen. So let me show you what we've got. In solution right now is the buffer, and we have acetic acid, and you got sodium acetate. Okay, so that's what our buffer is made up of. What we're adding into it is sodium hydroxide. So sodium hydroxide is a base. So the base will chemically react with one of these two. Bases don't react with other basic salts. Bases react with acid, so it's going to react with the acid part of my buffer. So I'm going to start out with the acid. And you're going to write a reaction with the base. We're going to draw one arrow. One arrow means this thing's going to go to completion. Double displacement, so you're going to make water. And you're going to make sodium acetate. Okay. And you could do a net ionic of this. Net ionic, this is going to be important later. This would be my spectator here. Water would box, acetic acid would box. So we're going to do not a Rice table, it's actually called a RICA table. This is something my students made up several years ago. The R's reaction, I's initial, C's change. A is actually stands for after the reaction. And the difference between a RICA table and a Rice table is that, first off, our unit's going to be moles. Another thing is, instead of everybody having a number in equilibrium, somebody's actually going to go to 0. So that's kind of a big deal. And we have one arrow instead of 2 arrows. Alright, so we're going to begin. We have 0.3 moles of this guy. We're putting in 0.1 moles of that. In the beginning, we don't really care about water. There was water there in the beginning and the end. And there was actually sodium acetate there as well. He's just not chemically reacting, but he is there. And the job of the buffer is to make whatever I add into it go away. So it's to make the smallest number here go away. So I'm going to subtract 0.1 moles here, because I want it to go to 0. That's why it's an A and not an E. Equilibrium, there would be something still there. So he's at 0. Basically, this reacted to make that go away. Now you can go past your buffer capacity as if you had added 0.4. Well, now the smallest amount, so now you'd be making the buffer go away. That's when you start killing yourself, is when you go past your buffer capacity of like your blood, etc. So if he's 0.1, this is a 1-to-1, then this would be minusing 0.1. Notice it's moles, so you get 0.2 moles. If you subtract on that side, you're going to add on this side. Okay, so now after the reaction, we're going to see what's left in the container. There's no more OH left in the container, but you've got a weak acid, and you've got a conjugate base. So if you can recognize that, oh, that's what I've got left, I can now use the Henderson-Hasselbalch equation. Negative log of the Ka, which was 1.8 to the negative fifth, plus the log, the base. Which one's the base? Well, this one's acetic acid. This is his conjugate base. So you have 0.4 moles over 0.2 moles. And you just plug that in. So you should find that this pH is around 5.0. Or 5.1, 5.05 I think is what we actually got. Okay, so that's that one. So we're going to do the one underneath it. And so let me just, I'm going to get a new page here. For the B part, I'm going to scratch through that. I'm going to work it up here just because I don't have enough room. This is my B. This time I'm going to add hydrochloric acid in. Remember what we had in our buffer? We had acetic acid, and we had sodium acetate. Now we're going to add hydrochloric acid. Well, it's going to react with one of those. This is an acid, so it will not chemically react with the acid part. It will react with the base part. Well, it just so happens to be a basic salt, so we're going to start out with hemp. We're going to write plus our acid, which is hydrochloric acid. One arrow, double displacement, so you're going to end up with acetic acid. And you're going to end up with NaCl. If we do the net onyx, let me just switch colors here. This will slash, and this is going to be our spectators. This will also slash. Can you see what NaCl is going to be doing? It's just going to be spectating. So instead of a rice table, we're doing a Ricca table. So we're going to be using moles. One arrow. So this guy starts out with 0.3 moles. This is going to start at 0.15 moles. This started out as 0.3 moles as well. And in the beginning, we really had 0 of this. You could put 0, but this is like water. It's just kind of spectating. It's there, and we're going to make some more of it, but it's just, we don't really care about it because it's not going to affect the pH is why we don't care. Alright, smallest number go away on the reactant side. This is our smallest. This is one way you could have done a limited reagent problem. So he's going to 0. That's right, 0.15 moles. You get 0.15. And if you subtract on this side, you add on this side. Alright, so now we're done with that. We're going to look and see what we got. We've got acetic acid and sodium acetate. So that's a salt. That's a weak base. We can use Henderson-Hasselbalch. So we will take negative log of 1.8 times 10 to the negative fifth is our Ka. pKa is what that is, plus the log. And our base this time is over here, 0.15 moles divided by 0.45 moles. And we will find the pH for this one to be 4.26. So we added a really strong acid and quite a bit of it to it, and our pH went from a 4.7 to 4.2. It's not much. We had a pretty strong base to it. It went up just slightly. So you can see buffers resist change. Well, there can still be a time where just one little drop will send the buffer way to the point where it can't recuperate. So that's what we're going to be looking in our next part. So that's all the lesson, and I have uploaded on Edmodo your assignment. So hopefully this did help you.